Okay. Well, anyways, yeah. So we're Team 14204, the Super Scream Bros, and we're gonna be talking about prototyping and design today. So, we're gonna be talking about prototyping and design from the point of view of our engineering design process. This process helps us transition from concepts and ideas to physical designs and builds. So, our engineering design process consists of 6 steps: research, concept, design, build, test, and improve. And yeah, we're just going to start it off with research.
All right. Re- I went too far. There we go. So, research is often the first step in a successful design process. It can help you come up with new ideas and learn more and expand upon ideas that you already have. Some examples we have of places we like to research is from other teams on YouTube, Facebook, Reddit. They like to post a lot about their own accomplishments and designs that they've done. We also like to look a lot at real world concepts and from experts in the real world. Some examples we have are other teams. We For one robot we had during Skystone, we were inspired by a robot in the Vex robotics competition, which is similar to FTC. And we also love to look at other teams' Robot in 3 days live streams and videos. It's just where they build a concept robot in 3 days approximately after the game release. Some real world concepts we also have is automobiles like a differential in a car, construction machinery like a scissor lift, and we also have talked to two professionals such as Mag Switch and Sunbelt Rentals for their opinions on some designs. Previous seasons can also be super helpful. You can get ideas from them. So during the FTC season Ultimate Goal, we had to these phone things, and never done that before. But thankfully, FRC had done that before. They launched frisbees for one of their challenges, and so we were able to look at some of their designs to kind of get some inspiration on how to accomplish our task. And as you can see, there are two pictures of FTC right there. One is from Rover Ruckus, and the other is from last year's challenge, Freight Frenzy. And as you can see, the game elements are reused. Game elements reused from time to time. And so if you've worked on them before, you use previous ideas that have come up for gathering and processing elements. All right. One saying we have is sacrifice for originality. What that means is that making a complex original mechanism can be really cool, but sometimes there is a more simple and effective alternative that is a better option. And ideas are not set in stone. So if you find an idea from another team and you see ways to improve upon it, that's okay. It's okay to improve upon other people's ideas. So always be on the lookout for ideas at meets and competitions. Also, after your initial concepts have been thoroughly researched, do not stop researching. You may come across new and better ideas that just completely blow your old ones out of the water. You might find ways to improve upon your current idea, and you might also see other people using your exact idea, which kind of helps reassure you that you are actually using a good idea.
Okay, the next step we have in our design process is concept. We use whiteboards to sketch our ideas. We turn those ideas into designs, and we would like to receive as many inputs as possible so that we can have lots of ideas. Sketching allows for sharing of ideas to refine your concept so you can make your ideas better. We also brainstorm ideas. Our ideas can be taken from the research stage, or just we can have new ideas. We also say that no idea is a bad idea, so any idea can lead to your best idea. The ideas also need to comply with the season strategy and season rules. Ideas can come from a unique season strategy, and one example is last year in Freight Frenzy, going around the barriers and over them. So we built a tall and narrow robot so that we could do both of those tasks. And that influenced the design of our chassis.
After sketching, you might begin to start prototyping, and so you can use foam board, plywood, tape, window slats, rubber bands, tubing, old game pieces for some of your prototyping stages, just trying to get your designs out quickly so you can do some basic testing. We also might repurpose old parts for testing that we used in previous seasons. And sometimes we also concept with GoBuilda, Rev, Actobotics, or any other build system, even if it isn't the most effective option or most specific option to what we're using. We also sometimes, in the prototyping stage, test with motors, servos, and with just simple programming in order to gauge the movement that we want to see. Next slide. And we also might perform some calculations in the prototype stage. So for instance, some of these calculations might be motor speed, gear ratios, we might calculate dimensions of the part, or the angles that they might move. But this is not always necessary during the concept stage, and at times, trial and error may be more effective. And once again, do not stop searching. Always find ideas may blow your own out of the water, or take your concept you already have to the next level.
All right, next category is CAD design. Come on. So CAD stands for computer-aided design, which pretty much means making 3D models using a computer. Some various CAD programs such as 360, SolidWorks, Onshape, and Creo. Our team uses Fusion 360 specifically as a reference, but for FTC. One good thing with CAD is that it helps reduce iterations. For this, we have an example of our fake ramp design from last year. You can see a robot. It's a complicated design because it does a lot of things. It sets the width of the robot. It's attached to the robot, multiple surfaces and multiple planes. And the ramp, the arc ramp, is to be the same as the wheel you take. That's also kind of complex to design. And we are able to do multiple iterations in CAD and over several months. And the first that we did, we were able to function as we needed it to, and actually only needed to make one change to it during the season. That was because we wanted to change the robot. All right.
CAD is for custom manufacturing, such as 3D printing, CNC routing, laser cutting, etc. Public makerspace is available everywhere nowadays. The team is interested into manufacturing your own parts. A good thing about CAD, you can rely on your own parts and not pre-made parts, allowing you to customize your robot more easily. CAD models can also be used to make a list with limits on unnecessary purchases. Also, for more precise calculations to less failures. Websites have CAD models of their parts on the web, which makes designing your robots and bits easier.
All right. So another thing CAD is good for it helps guide the order of assembly. So for this, we have our tape measure design, which pretty much tools tape measure brings it back. So what we would normally do would be attach the metal servo horn to the servos, and then put the servo onto the mount for the servos, and then attach that to the tool. If you did that, you won't be able to put servos on into the mount. So what we need to do here, and we use Fusion to figure this out, CAD. We have to screw the servo horn to the spool first, and put that in, and then the two servos in next. Otherwise, you just won't be able to get it together. And another thing is that the simple ideal design. This article here is all rollers from last year. Up top, you have the metal design used to go build, and so this has a lot of parts. So it was really complex, and it was hard to build, and pretty likely to build, and it was also a lot heavy because of we switched to a printed design, which you can on the robot as well. And this was very little parts comparatively, and it didn't as often, and it was a lot lighter and easier to assemble as well. And back. Then it was also easier to edit it because it was more simple, and you can see in the bottom photo there's a distance sensor, and it made it a lot easier considering it was a much simpler design at that point. Alright, and also very complex designs CAD is good for. So you can see we have our top level design, this being our entire robot modeled in and you can see within this model we have the intake here. And that intake is part of what we call a subassembly. And so this is a completely separate model which we added to the big chassis robot design. And from that we have this model, which is the intake ramp, which we then put into this one. So that's how you do top level design, which I mean that's pretty much how I explained, and that helps for making organized and large and like multi-piece designs.
Our next step in our design process is build. In build, we'll be covering tips for building our robots, or your robots. So, our first tip is that set screws have a high failure rate. This can cause a drive failure, which can be bad. Our solution to this failure mode with an axle spacer in the top left there, that's our solution. You can also Loctite it to reduce the chances of coming loose. This is also useful for areas like right here is a cross section of a motor. It can be useful for Loctiting stuff in that area, making you have to repair it less. Our third tip is attaching parts at multiple points. Minimum of 3 screws is really needed to cause this, and it eliminates all movement of freedom for a single part. So right here, we have 4 screws in this piece, which eliminates all freedom for the part to move if it were to be hit. And then, don't stop researching. You can find a new, better idea.
So yeah, the next one in our design process is testing. We're going to share some strategies that we like to use to make sure that our testing is effective. One of our strategies is the 10 times test, which basically states that if your design is able to consistently complete its task 10 times in a row, that proves that it's a design that is robust and also reliable, which is exactly what you want in a competition setting. Another one of our strategies is making data-driven decisions. In robotics, it's really easy to get tied to your first design because you're proud of it or because you worked really hard on it, but we really try to take all emotion out of our decision making and make things based on objective data rather than on how much you like it. We like to say, don't get married to your design. So one example of us doing that was with our intake from last year. He made tons of intakes last year, and instead of just sticking with his first one because he was proud of it because he worked really hard on it, he tested each one and proved that the one that we ended up with was indeed the best design. And whenever you test, it's really important to use your observation skills and ask yourself questions that really spur improvement. So it's important to recognize what's wrong, obviously, but also it's equally as important to recognize what's going well and how you can improve it for next time. So ask yourself those important questions. One last thing that we like to do whenever we test our robots is building multiple robots. So whenever we have a second robot, it allows us to implement our designs quicker and more than one new design all at once. So instead of having to fix one part and take apart the entire robot, fix that part and put it all back together, you can start from scratch with many new designs all at once on the second robot. This also allows for a second robot for backups, just in case anything goes wrong with your first robot, and also allows us to have a spare robot to test programming on whenever the programmers need to test any of the things that they're creating. One thing that you need to keep in mind, though, is that you are only allowed to bring one robot to the competition. So if you end up using this strategy, please don't bring 2 robots to a competition because you will definitely get disqualified. So don't do that. And next up is improve.
So, ways to improve. You first start with a cycle to get to improve. Each step so for concept, you can redesign and sketches and prototypes. Design, you would improve upon your 3D designs, your calculations, and your parts list, building your reassemble program and buy parts. Then test, you would gather data and troubleshoot. Now, you can always go back to any part in the process. You do not always have to start from the beginning. Another way that you can improve is to use Elon Musk's design method. So, first step would be to make requirements list. You might have one way at the beginning to reach a certain goal, but you might realize as you go through that it's just a roundabout way to get to a certain goal, and your requirements might change. Then you will delete a part or process to make a part simpler or easier. Simplify or optimize the design to make the design easier, simpler, and lighter. Then accelerate cycle time, so you'll start to increase the cycle time of improving, but do not go faster if you feel like you're just digging yourself into a hole. Automate, then you'll eventually just continue this in a faster cycle. Then you will never stop improving until you reach a deadline.
But yeah, thank you guys for listening. Do you have any questions? We're free to answer them. So. Yes. What was your question?
So how many you actually built for a season?
This past season we built 2. Okay, we built 3 last year.
We only had to go at the end of the season. Oh, okay, thank you. We built 3, but we built 1 like at the very beginning of the season, and then as we moved on through that season, we realized that we didn't really need that one from the beginning because we already had a second one. So we took it apart and took some of the materials from that one to build our newest one. Yes.
Yeah, we could probably do a little bit. We don't have any like tennis balls or anything to cycle through it, but
Oh yeah, that sucks.
Give it a second, the driver hub's
yeah, driver hub's turning on. But I can probably just explain some of the basic operations. So this was a robot for freight frenzy. First step is it intakes balls and blocks that you saw in that picture. Kind of flings them up this ramp and then into this bucket. This bucket then goes into this linear slide.
That's fine. Just keep pulling up. You're good.
It goes into this linear slide. It can go to any of the height levels on the little tower that it had that year. And then the servo can lower down. And then Dr. Ball or block falls out.
then you can bump it down.
Yeah, just 1 moment. Alright, there we go. Should get going in a second.
Quick question if I can while we're waiting.
Yeah.
Do you guys have any tips for specifically for the prototypes and how to minimize cost and expense on building prototypes?
So one thing that we like to do is we make very quick CAD models. Well, like you can use like 3D printing and whatever during the prototype phase as well. It does take a little bit longer, but if you can get around to it, that does help. But also, Ben has an example.
Yep. So this right here is just foam board on top of some Go Build It components. Oh, there's also a 3D printed part there. 3D printing is great for prototyping if you have a little bit more time. This was 100% foam at one point, and it did technically work. It wasn't the greatest, but it did kind of prove our concept.
What material is that right there?
This right here, the top part right here is still foam board, but down here this is PLA plastic from a 3D printer. Yep. Any other questions?
How many of you know CAD well in the team?
Me, him.
You guys can raise your hands if you'd like.
Yeah, raise your hand.
Sure.
I know. Wow.
You probably
Impressive.
Yeah.
pretty much most of our builders know CAD because it's really helpful for being a builder. But typically, like programmers and stuff, we won't, they don't learn CAD as much just because they're programming, not doing building.
Why don't you say how that many of you learned how to do CAD? Because somebody out there, I mean, everybody at first knows what CAD is, but what way did you guys learn how to do it? What's the most efficient way for the people to learn CAD?
I'd say we learned a lot from one of our mentors who works at an engineering company and uses CAD on a daily basis, so he kind of taught us what he knows. We also used a lot of guides from Fusion 360. They actually have a bunch out on YouTube that are very good. So yeah, I think that's our main way, right?
Another thing that you can do is use Tinkercad. If you've ever heard of that, that's a completely online system, and it's really easy to pick up. And so that could be really helpful for learning like the fundamentals of CAD. And then you could move on to a more complex program like Fusion or one of the other ones that we showed for that can make slightly more complex designs. I guess, I don't know.
Any other question? Oh.
Can you show some of those parts you mentioned in the presentation, like the wall rollers and that kind of stuff? Because it's hard to see them from over here.
Yes.
So the wall rollers are right here on our robot.
You can maybe like bring the robot up there a little bit. You can carry it around.
Explain what they're used for, maybe too.
Yeah. So what do you want to explain that? You got it. Okay. So what they did is whenever we went to last year, there's like some pipes and then the wall and then like a 13-inch gap in between them. So the idea was that you'd just have the wheels just go on the wall so that you could just hit the wall and slide across it without like damaging the wall or your robot or anything, because that gap was really narrow and it was easy to hit the pipes if you didn't go far enough over, and so that made it a lot easier to get through that area as efficiently as possible. So the thing about the ramp is it is really low, and sometimes we do scrape tape off the mat, but it doesn't hit pipes or anything because the whole area that's like anywhere near the ground is all within the area that the wheel is, like the ground wheel. So if we were to hit something with this wheel, it'd like bump up, and then it wouldn't be able to hit the mat.
Yep.
So like when we were going over the pipes last year, we'd just go over it, the robot would be lifted up, and then so would the ramp.
Yep. So anything that hits both of those wheels will not be able to hit the.
Did you have to refine that to, at the beginning were you too low and then you had to shave some off?
I don't think we did. I think we just got really lucky that we didn't have to shave any off. But I was talking about that. We iterated a lot on that with the in CAD. So we thought about that a lot and were able to figure that out. Because the way we designed it, I don't think we have a photo, and we don't have Fusion, so that sucks. But basically the way we designed it is we made, in Fusion, you make the sketches. So we had multiple circles, and we had a circle that would represent the wheel, like the drive wheel, and one that would represent the intake wheels. So the idea was that we kept the bottom of the ramp in the area that the drive wheels were, because we could see that because we had that bigger circle that represented these drive wheels. Am I making sense?
I think so.
Okay.
Alright, any other questions?
So for the intake, I saw you did the 3D print.
Mm-hmm.
But you're gonna hit that all the time. Isn't that gonna grow? Why are you using 3D print parts for intake? Do you guys ever know in competition?
Well, it's TPU.
Yeah, we use TPU, which flexes.
The ramp, I think.
Oh, you're talking.
No, I'm talking about the intake, the green one. The red one.
So the red ones are not actually 3D printed. The red ones are actually from AndyMark.
Are you talking about the ramp part, like the part that actually slopes up?
Oh, that one, intake is not sticking out, right? Stay there all the time, is it? Your intake, I cannot see.
Okay. Yeah, Owen. Thank you. Thank you, Owen. Okay, so
It's flexible. It doesn't. It's not hard.
yeah.
This is our ramp.
Got
And
it.
this is a 3D printed resin wheel and two AndyMark wheels.
I see. Okay, that makes sense.
How many different materials do you 3D print with?
We 3D print with about 3, maybe 4. Yeah, I would say there's 4 different types of printing material on this robot. Being actually, there's probably no PLA, but we use PLA to prototype because it's a lot cheaper than the other filament that we use, which is called PETG. PETG is it's a lot better than PLA in some cases, of course, because it flexes more and it's stronger. So whenever you like hit it on something, you're not as likely to just snap it like you are with PLA, because PLA is actually quite brittle. So that's why we use TPU primarily, but we use PLA for like prototyping and stuff because it's a lot cheaper.
You mean we use PETG primarily?
Yes, we use PETG primarily because it's cheaper than PLA. No, it's more expensive than PLA, but it's stronger. PLA is cheap, so that's why we prototype with it. And then we also are fortunate enough to have access to a resin printer. So with the resins, you can actually print flexible stuff. And so we have the center wheel on the intake. Can we go back in the slides to? Yeah, keep going, keep going. Getting close. Oh, yep, here we go. You can't see that at all. Okay. So there's 3 wheels here. The 2 red ones are from Andy Mark. We just bought those. We actually cut off half the spokes because there's 10 and there's too many. So we cut off half of them. But then this one in the middle is resin printed. And so what it is it's called it's just called like flexible resin. They don't have the same naming scheme as they do for. Yeah. So it's flexible, so you can see it can kind of flex, and so that's really good. And it's also quite stiff still. So it's good for what we use this for is the red wheels, like pick up the elements, and then we use this big one in the middle to actually push them up the ramp, because the ramp it goes to full. You have to go like fully vertical at the end of it because it's like an arc.
Yep.
It's like flexible resin.
Do you buy it? Do you, I mean, how does one acquire? I'm thinking about new teams all the time.
Yeah, so it's what's the type of printer that we have?
Oh, I don't remember.
We are also getting a cutoff right now.
So
Oh.
the resin's good with the type of printer that you have. So we buy the brand that goes with our printers.
Okay.
Yeah, thank you guys so much.
Yep,
I
thank
think
you.
that we're running out of time, so thank you so much for listening. Good job.
Good job.